All right, exponential functions are functions where the variable is in the exponent, okay? Instead of as a multiplier, it's exponential. The C that you see there in the front, we call that the initial value. If you're applying this to bacterial growth or something like that, it's your original population. So that initial value, what the population is at day 0, is how you look at that. That A there is the growth factor or the decay factor. So it's growth / decay factor. Depending on what number it is, whether it's growth or decay. Whatever A is there, that's your factor of growth or factor of decay. And so what we're going to start out doing is building a exponential function based on a set of ordered pairs. And how do you recognize if something is exponential versus linear versus quadratic or more of a polynomial type shape? And so let's look at that. So instructions would be is the set of ordered pairs exponential. If so, write the exponential equation. Let's start with something. Just set of ordered pairs, x and y, 0, 5, 1, 10, 2, 20, 3, 40, 4, 80. How do you determine if something is exponential versus linear or quadratic or something like that? Well, linear is easy to tell because you can find the slope between sets of ordered pairs. And if the slope's the same between any two different sets, then it's probably linear. You could also plot these points on a scatter plot and see what kind of shape it makes. That's going to help you as well. So you know how to do that with your graphic calculator. List 1, list 2, plot that. You can see that shape happening. Mathematically, you can look at the ratio of y values. So notice how the x values here are going by the same increment there. That makes this a little easier to do because if I take the second y value over the first one, 10 over 5, I get 2. And then 20 over 10 is also 2. 40 over 20, also 2. 80 over 40, also 2. That's a ratio of the y values. That ratio, if it's consistent, then that's exponential, and that value right there is considered your growth factor. This is a growth factor because it's a positive whole number or larger number. Doesn't necessarily have to be a whole number. It could be a fraction, but it's got to be a larger fraction, something bigger than 1. So growth factor is bigger than 1. Decay factor will be a small fraction between 0 and 1. That's the difference in growth and decay. So ratio of the y values as you go down, second over first, third over second, that way of going about that to determine if those are exponential.
So then they all have to
Yes. Yeah. For that to be your growth factor, yes. Now there will be time. We'll look at something with our calculator in the next section where we're actually taking a set of real world data and asking the calculator to create us an exponential function with that. That may not exactly be the same ratio, but it'll be really close out of that. But here, these are going to work out beautifully for you. They're not. I wouldn't consider these real world data, most likely. It's made up theory math stuff that works out pretty, because we're trying to learn that idea. But as if we get some real world data, we'll use the calculator to help us find that growth factor instead of doing it by hand there. So growth factor, we know as x gets bigger, y is increasing really fast. So it increased 5 in that first step, it increased 10 the second step, increased 20 the third step, 40 the fourth step there. So it goes up fast. So that we know that graph is going to look something like this. That's what an exponential growth graph is going to look like. Is that the equation of that? Remember the form. Well, if we know the growth factor is 2 because we did the ratio of the y values, then the a we're going to replace with a 2. We got to find out what c is. And c is your initial value, and your initial value is going to happen at x of being 0. We happen to have that ordered pair here, but if we didn't have that ordered pair, we could find it just by plugging in some information. Plug in 0 for x and work it out if we did that. But we have that ordered pair here, so we know y is 5 when x is 0. What's anything to the 0 power? 1. So we end up with 1 times c equals 5. So that means c is equal to 5. So our exponential function for this particular thing, instead of c, it's 5 times 2 to the x. And you can plug in those x values that are here and see if it got you the right y value, and it does. So we're going to find the growth factor or decay factor, depending on what it is, what that value is, by the ratio of the y values, and then we're going to find out what c is by using that ordered pair with that going within. Well, you actually could use any ordered pair if you wanted to. The 0 one is the easiest one. Let's look at another set of ordered pairs. Let's say -1, 32, 1, 8, 2, 4, 3, 2. If this one is exponential, what do we expect it to be, growth or decay? Why? Smaller. Y values are getting smaller as x is getting bigger. So we think this is decay if it is exponential. So if we test for exponential, remember second one over the first one, which reduces to be 1/4. Not 1/4. Hold on. Why can I not do 8 over 32? Well, not necessarily because it's decay, but look at our increments here. From -1 to 1 is how far of a jump on x? 2, but the rest of them are only 1. So that ratio, there's a missing piece in there. There's an ordered pair that's, the 0 something, 16 is what it should be there. If we follow the pattern, we can recognize that. But that ordered pair is not there. So that ratio, you got to watch out for that. They'll leave one out every now and then. So, we'll start with 4 over 8. That's 1/2. And then 2 over 4 is 1/2. We only get 2 of them there, but they're both the same. Most likely it is exponential. And that your decay factor is 1/2 out of that. So f of x equals c times 1/2 to the x power. And then we need to find out what the c value is. So we pick an ordered pair to plug in. It doesn't matter which one you pick. I usually like to use x being 0 or x being 1, whichever one I have. I have an x being 1. So I'm going to use 1 as an x and 8 as the y. So 8 equals c times 1/2 to the first power, which to the first power is really easy to work out. It's 1/2. And then solve it for c. So multiply by 2, and we see that ordered pair that Hunter told us about is 0, 16. So our initial value was 16. So f of x 16 times 1/2 the x power. Not going to get super complicated in this section as far as finding the equation of that. I'm not going to give you one that's got a weird addition or subtraction or strange multiplier on the front there. It's really that process over. As we get into the next couple of sections, we'll talk about using the calculator to help us find an equation of a much more complex set of ordered pairs. Use some technology to help us there. So really, really easy idea. Let's bring back some stuff from chapter 3, because we do that in every chapter. Just describe the transformation on y equals 2 to the x. So that's our parent function, is 2 to the x. And say f of x is equal to 2 to the x plus 4. What transformation is that? What does it do to that graph? Up 4, because the 4 is where? It's outside. It's not up there with the x. So this is an up 4 units. We'll let that be number 1. We'll just do a few examples here. F of x is equal to 2 to the x minus 4. Similar, that would be to the right 4. It's with the x there. 3 f of x is equal to 2 to the negative x minus 5. Good. Reflect across the y-axis because of the negative on the x, and then down 5. And again, guys, you got a graphic calculator in hand. You can graph the original and then graph the one they give you, see what happens to it. You know, that sort of thing. Don't forget you've got some technology can help you out. It takes a little longer to do that than it does to just remember the rules, but some of you have the rules down pat, so you don't even have to think about it too hard to do that. Okay, so resurrecting some things from chapter 3, because we got to always roll that back in with every type of function that we deal with out of that. So the next thing is something that I think you'll enjoy much more than some of the other things that we've done: solving equations. We like solving equations a little bit more than we do other things, because you get an answer and there's some finality to it, and you can take that answer and check it if you need to. Okay, so that's always what I've noticed with algebra students is we like it when we solve an equation and it's not so much theory as it is actual work. Feel like you're doing something. Solve exponential equations. And we're going to start with today. They're fairly simple equations. The idea is to think exponentially, and instead of thinking more along the idea of what times this gets me that, it's think how can I rewrite this number as a power? That's kind of what you got to think. That's what I mean by think exponentially. So if you had a problem, 2 to the x plus 5 is equal to 2 to the 8th. What do we know about this equation?
Whatever x plus 5 is,
It's got to equal what? 8. Because we have an exponential equation here because the variable's in the exponent. One side has a base of 2, the other side has a base of 2. So if they're both base 2s, then the exponents have got to be equal to each other, right? So this is what we're going to have to end up making the problem look like. So solving that, you'd be x plus 5 equals 8. So the equation you're going to do, x has got to be 3. We know that, just real basic 7th grade equation once you get past the exponential part. And this is where the thinking exponentially comes in. When they throw you an equation, it looks similar to that one, but it's not quite the same. We have 2 to the x plus 1 is equal to 16. The bases aren't the same on this one. So what we've got to think here and think exponentially is, can I rewrite one of those sides to have the same base? 2 to the x plus 1, there's really not a lot I can do to that. But 16, it'd be 2 to the 4th power, because it's 2. If I break down 16, it'd be 4 and 4, 2 and 2, 2 and 2. So that's 2 to the fourth power. So that's how we're coming up with that, if you're unsure of that. Should have done this in Algebra 2, I hope. Some, at least. So, and then our equation, x plus 1 is equal to 4, so x has got to be 3 again. Wonderful. Remember that. So not too difficult there. Just got to think a little bit on a different scale. Let's say we had 3 to the 5x is equal to 81. So if we're thinking exponentially, because the variable's in the exponent, that's what tells us to do this. 3 is a prime number. You can't break it down any further, right? So, but 81 can be broken down into what? It's 3 to the 4th power. And as you've done more of these, the more of them you'll recognize and be able to spout off without having to do a factor tree or anything. But 5x is equal to 3 to the 4th. So our equation that we set up is 5x is equal to 4. Solve that for x. And we get a fraction for an answer. And that's quite okay. Because we know when we plug that back in, 5 times 4 over 5 gives us 4. And we know 3 to the 4th power is 81. That's right. Okay. Where folks, most of the time, those first 3 equations, everybody gets those. That's easy stuff. Where folks start having trouble is when we have a problem like this. And it's not because the numbers are super complicated. It's because they don't think exponentially. They think about what's the relationship between 4 and 8. 4 times 8 or 4 times 2 is 8, right? But that's not exponential thinking. That's multiplicative thinking. So think about 2 squared is 4, right? And 8 is 2 to the 3rd. So if we rewrite that problem, 2 squared to the 2x minus 1 equals 2 cubed. Now I have a problem that has the same base on each side. So I want the bases to be the same. It makes it so much easier if the bases are the same. And then what's the rule for those exponents right there? Multiply them. That's right. Anytime we're taking something and raising it to a power, any exponent that's already there is going to multiply. So we're going to multiply 2 times 2x minus 1, which will be 2 to the 4x minus 2. It's equal to 2 to the 3rd. Our equation then becomes 4x minus 2 is equal to 3. Solve that equation. 4x equals 5. Divide by 4. We get a fraction again. 5 over 4 this time. And that's going to end up giving us nice little. And because the variable is in the exponent, it's related to that. And you could have basically one side would be like your function f of x is equal to this. The other side is your y value. It'd be like finding the x value for a given y value. So like if they gave you a y value, you needed the x value for it, you'd set up an equation like this to do that. So that's the relationship there. It's almost kind of there's almost a line between the stuff there that you're not doing a whole lot of graph with this sort of thing. All right. Let's look at another one. J 27 is equal to 9 to the 2x. What do we know about those? Okay, so 27 is 3 to the 3rd. 9 is 3 squared. That ends up being 3 equals 4x. Divide. Pretty basic and simple. The 4x came from 2x times 2. If you're unsure where that came from. See what we remember about that. Nine to the 5x equals 1 over 27. So that's very similar to example J, but not quite. So on the left side, I know that that can be 3 squared, right? How can I rewrite 1 over 27? Good job. 27 is 3 to the negative 3. Those negative exponents. Anytime that number's in the denominator, that's where your negative exponent's going to come from. Out of that. So that's going to be 3 to the 10x, 3 to the negative 3. So 10x is negative 3, negative 3/10. Not bad. Just got to think about negative exponents. Anytime it's a fraction at the original equation, you got to know, hey, that's going to probably be a negative exponent. So I got to think about it in that way. Help you out a little bit. 4 to the 3x squared is equal to 8 to the x. A little bit more complicated equations to work with here. We've already dealt with 4 and 8 being on each side, so we know to change them to what? 2's. 2 squared and 2 to the third. So that's 2 squared to the 3x squared, 2 cubed to the x. That's going to give us 2 to the 6x squared is equal to 2 to the 3x. So our equation then is 6x squared is equal to 3x. How in the world do you solve that? No, you can't divide by x. X could be 0. And if x is 0, you can't divide by it. How can I factor it? Get it equal to what? 0. So I'm going to move the 3x by subtraction. And then that, by getting it equal to 0, that opens up things for a quadratic, because this is quadratic because it's got x squared in it, right? So we got quadratic formula, we got factoring, maybe square roots. This one doesn't do that, but factoring would be the quickest way on this one. GCF of those two would be 3x, right? And that'd leave us 2x minus 1, and we set those equal to 0. So x is equal to 0, and x is equal to 1/2. Two solutions to that one. You plug those into the original problem to check them. They both work for this one. Again, we want to check those if we can. So anytime you end up with an exponent on your variable, you want to get it equal to 0 to solve it. If it's squared, cubed, anything like that, you want to get it equal to 0 to solve. Opens up factoring, and especially if it's quadratic, it opens up quadratic formula and all those things there. So be careful of that. That's a key thing. E to the 2x is equal to e to the x minus 1. E is a number. The exponential number, what it's the E stands for. E to the first power is about 2.71 and a whole bunch of decimals after that. It's kind of like pi. It's one of those numbers that's been around and used enough that it got its own symbol or letter in this case. So we just say e to the 2x is equal to e to the x minus 1. Does that change how this problem works? No, the bases are the same on each side. The good thing is there's really nothing I can do to manipulate an e, so I don't have to worry about fixing the bases when it's an e in there. So it's 2x is equal to x minus 1. Solve that. Get x is negative 1 just by subtracting that x. Let me get that. Not too difficult. They throw that E in there. Don't get sidetracked on it. It's easy. So it's so easy. Let's make a hard problem out of it. E to the 7x times e to the x squared is equal to e to the negative 12. So we got to think exponentially here. So exponent rules and all those things are all in the game here. So anybody tell me what to do with it? Do I multiply 7x times x squared? Why do I add? Yeah, it's multiplying a power times a power, and the rule for that is add the exponents. So we would, on the left side, we end up with e to the x squared plus 7x, and I just wrote in that order because that's the way we normally write a polynomial, in descending order. And on the other side, we got e to the negative 12. Hey, we got the bases the same now. So we've combined one side into a single power, and that allows us to set up the equation x squared plus 7x is equal to negative 12 and solve that. So what do we do to solve that equation? Make it a quadratic by adding 12 x squared plus 7x plus 12 is equal to 0. And then you've got options. You can factor. You can use quadratic formula if you want to. If you want to complete the square, be my guest. Go ahead and do that. I'm going to factor that using the X method because I've done that one enough times. 12, 7 is 4 and 3. So that'd be x plus 4, x plus 3. Set those equal to 0. Negative 4, negative 3 are two answers. If you plug those back in the original, it works out there. On your calculator, the E, if you were going to check your answers there, the E, to get that, you hit second, and then down here on the left-hand side, there's an LN button, and right above that in blue, it says E. So if I needed to do E to the 7 times negative 4, and then E, then negative 4 squared would be 16. It's that number. Oh, well, that's supposed to be e to the negative 12. E to the negative 12. We'll see if that's that number. And it is. So the E is on the left-hand side, right below the log button. So it's the LN button. Second LN gets you the E if you needed to check some numbers there, just to make sure you're getting the right answers out of that. And kind of my brain's been thinking about Amanda's question, or how does this relate back to the graph and the exponential growth and decay? Here's an interesting thing. If you take this equations and graph each side separately, and this is an interesting way of approaching solving an equation. It's a valid way if you don't know how to work it algebraically. So let's say we had, go back to example F, the first equation that we had, the 2 to the x plus 5. So if I put that in here, 2 raised to the x plus 5, I see a growth graph right there, right? And then on y2, if I put in the other side of the equation, which in ours it was 2 to the 8, which is just a number. I can't see that on this particular page. I'm going to have to zoom out a lot. One more time, I think we'll do it. One more time. That's that number. There it is. Notice they're crossing. Where they cross is the answer we found for x. That ordered pair where they intersect out of that. So how does it relate? It relates in that way that you've got a growth equation or decay equation on either side. And the graphs of those the intersection of one side should be with the other side on the graph. That's if you're on ACT or something, and this is probably good information to give you before last Tuesday. You could graph both sides of the equation as separate equations on your calculator and see where they crossed, and that's going to be the answer. How would I find where they cross? Second calc, and then number 5 says intersect. First curve, second curve, and then there's my x value was 3. That's the solution that we found when we solved that equation, right? Now the y value is 256, but that doesn't really matter. I mean, that's what 2 to the 8th power is. It's 256, but the x value is the solution to the equation. So we're finding that. So your calculator, you hit second, trace, and then the intersection, and then just tell it which curves you want to. If you had like 4 or 5 different ones on there, that's the idea, that you could use several of them. First curve and second curve, and then hit enter, and it'll tell you. So it's really neat tool there that's available to you. This section is probably one of the easier ones in this chapter. Again, it's not unfamiliar ground because most of you should have done a good deal of this in Algebra 2. Kind of break it up a little bit. There's some sections of this that I don't want you working on. So 3 through 59, 61 through 84, and then 101 through 107 there at the end. Some application of that's what those are. But tomorrow work day, and then quiz on Wednesday, and then we'll play it by ear from there as far as the next section goes, because